So, eigenvectors and eigenvalues. This is actually a very easy idea and very useful. So what we're going to do is we are going to take a generic transformation matrix A. That's just a label I'm giving it. As an example though, we're going to use a reflection. So we're going to reflect all of our vectors in this vector space through the line L. Okay, so if we look for a moment at this blue vector and try to determine its image under reflection, or the output after this transformation, what we can do is take two sample points. So if we take the head of this blue vector and walk it perpendicular to the line of symmetry and then the same distance the other side, that gives us 1 point. And if we also do the same thing with its tail, so perpendicular distance to the line of symmetry and the same distance the other side, that gives us the image of the blue vector here. We can do the same thing with the red vector. So going from its head to the line of symmetry and then same distance the other side, and its tail is on the line of symmetry, so we won't be going any distance with that. Okay, so that's how you find the result of a reflection transformation through the line L. If we look for a moment at the green vector, this green vector is a very interesting case. So what happens is if we try to apply the reflection transformation, we get the green vector back. It doesn't change, doesn't alter. Its image is itself. Okay, this is an unusual vector, which we give a special name to, eigenvectors. This green vector is an eigenvector of the reflection transformation because its direction is the same before and after the transformation. Its direction has not altered. However, eigenvectors are a larger class of objects. They are vectors which remain pointing in the same direction after transformation, but they could scale, so they could increase in size or decrease in size. Scaling is permitted. So the most general class of eigenvectors are a solution to this problem here, where you apply a matrix A to a vector V and you get some scalar times the original vector. Now this scalar here, lambda, the Greek letter lambda, is what's called the eigenvalue. It's the scaling factor. So in our scenario here with the little green vector here, with under reflection transformation, lambda is actually equal to 1 because it's not scaled up or down, it's the same size as it was. Okay. So to find the eigenvectors and eigenvalues, we have a method, an algorithm for doing that, and it's as follows. If we rearrange this equation, we can say that this is the demand made upon the vector. Okay, now if we take the vector v out, this is what we're left with. Okay, and I'm going to put this lambda is just a scalar, so I'm going to multiply it by the identity matrix just so that we're dealing with only matrices in this in the parentheses here. Now, one condition that we also apply to eigenvectors is that eigenvectors cannot be 0. I mean, it's a trivial example, but if you look at this diagram over here, it's obvious that the 0 vector, its direction is not altered through transformation, but that's just a silly example. What we're really looking for is a vector v that after transformation, after the multiplication by the transformation matrix A, it results in a vector pointing in the same direction but scaled in some way. Okay, and this is the condition then. This is the condition. Now, if we come down here, we're going to apply this result to an example we've seen before. I'm going to take A to be the shear transformation, and that looks like this. So this shear transformation matrix describes this type of transformation here, where any vector along the x-axis is unchanged. The further up the y-axis that you go, the further it's pushed in, sheared to the right hand side. Okay, this is a horizontal shear. We're going to take this as our matrix A. Okay, here's the condition for an eigenvector, that the transformation matrix minus lambda times the identity multiplied by the vector v gives you 0. Now, in order for this matrix to be equal to 0, this transformation to be equal to 0, we require that its determinant is equal to 0. So recall that eigenvectors cannot be equal to 0. So this cannot be equal to 0. It must be that this expression here is equal to 0. But in order for this to be equal to 0, we demand that the determinant is equal to 0, for the reason that if we call this entire expression here q, for example, if we are able to multiply by some q inverse, then that will give us v equal to 0, which we don't want. So in order for this to hold true, in order for A minus lambda times the identity matrix to equal 0, which is what we want to happen, the matrix inverse cannot exist. And the only way a matrix inverse won't exist is if the determinant of Q does not exist. Okay, so that's the extra condition we're going to apply. Good. So we're going to take our matrix A as 1, m, 0, 1, minus lambda times the identity element, which is 1 minus lambda, m minus 0, 0, 1 minus lambda. And we make the demand that the determinant of this is equal to 0. In which case that's AD minus BC, so we get 1 minus lambda times 1 minus lambda minus m times 0 is 0. So we have 1 minus lambda squared is 0. So lambda is 1. That is equal to, that is our eigenvalue. An eigenvalue of lambda equals 1 makes sense because we're not scaling anything. A shear transformation involves no scaling whatsoever. If you recall that the area before and after is the same. So there's no scaling happening, it's just a shear. So our eigenvalue lambda is equal to 1. To find the eigenvector, what we can do is substitute lambda equal to 1 into our matrix here. So that will give us 1 minus 1, m, 0, 1 minus 1. And that is equal to 0, m, 0, 0. And we know that if we multiply this matrix, that's this matrix here, times v, our vector v, the answer is 0. So we multiply by the vector v, which will give components v1 and v2, and we know that the answer should be 0, 0. And if you do this multiplication, you get 0 times v1. It's 0 times v1 plus v2. 0 times v1 plus 0 times v2 is 0, 0. And so we have that mv2 is 0, 0. So that tells us that any vector that satisfies this condition is an eigenvector. Which means that the coordinate, its y-coordinate v2, is 0. That applies to any horizontal vector along the x-axis. For example, this one here. This vector has an x-coordinate, but its y-coordinate is 0. And this is an eigenvector, meaning its direction is unchanged during the transformation, which makes sense because the shear does not exist along the x-axis. So this all makes complete sense. I hope this concrete example makes this idea of eigenvectors and eigenvalues a little more understandable.